And I'm a software engineer at Facebook, and then Varun here is a software engineering manager at Facebook as well. And we're going to talk about spatial audio at Facebook. We both work on the audio team and the Audio 360 team. In the past, we've primarily been working on Audio 360 and the spatial audio. First of all, show of hands, even before this slide. Show of hands here. Who here is familiar with spatial audio and kind of the background? Okay, so we have a lot of hands. Good. So just so I kind of have a feel for the room, does anyone here kind of really feel like it's a new topic to them? Okay, so everyone's kind of, so we have a couple here. Okay, good. So if there was absolutely no one who was a newbie, then I would skip a little bit, but we'll make sure everyone gets to understand things. All right, so at Facebook, we have various tools and pipelines and things that are going on. So we kind of do everything, the whole stack. So I want to kind of break this down into pieces that we work on. So the first thing that we're going to talk about is the Spatial Workstation, which is a set of VST and AX plugins that we have available for content producers, sound designers, and so forth to prepare spatial audio. And then we allow people to upload videos to Facebook. So those videos are prepared with the Spatial Workstation. You upload those videos to Facebook or YouTube or whatever other platform would support it, or bake them into some kind of a VR application or et cetera. And so we'll talk a little bit about the Facebook encoding pipeline, transcoding pipeline, and so forth. And then, of course, once it's on the servers, it now needs to be streamed down to the users. And so we also need to talk about client playback and streaming delivery and that sort of thing. So we'll cover a few of those things in kind of in broad strokes, and then Varun is going to talk in more detail about the kind of the architecture of our spatial workstation and some of the things that we've learned along the way. Spatial audio is used in VR often, but it's also used in 360 videos, which are deliverable on all of these different platforms, both in VR, like the Gear VR or the Rift or any other headset, but also in desktop and Android and iOS. And so the way that this works is your I think we have an animation here. Yeah. So like your iOS device or your Android device, they're not being animated here, but as you move them around, it's like a window into your virtual reality, such as is going on in the Gear VR. Same with the desktop, you generally control that with a mouse or maybe a keyboard, control what you're looking at. And as you change your perspective, kind of the essence of spatial audio is as you change your perspective, as your head rotates, the audio then should also match the rotated, the way that your head is rotated, so that it sounds like it sounds in the real world. Because as I move my head around, whatever I'm hearing over there always comes from over there. It doesn't move around like if I'm wearing headphones. So that's what spatial audio is in essence. Now, there's lots of different terms floating around out there: 3D audio, surround sound, spatial audio, and then some kind of details around how these things are implemented. So 3D audio generally refers to game audio. This is the idea that there is a 3D space of some sort and audio is being rendered for that space. And so you may have objects moving around in the game, maybe even interactively, and those objects are being rendered as 3D audio. Surround sound, of course, is a speaker format, generally kind of with movies and that sort of thing, 5.1, 7.1. It is in some sense spatial, but it is not generally a term that's used for spatial audio per se. And then spatial audio is just a kind of a general umbrella term for including 3D audio for things that are spatialized or immersive. So we'll use the term spatial audio for the most part here. As far as implementation goes, in the sense of how do we make a spatial audio experience, we start with the idea of object-based audio, which came from games. You have these objects moving around, and any of those objects might be a sound source of some kind. And so they're going to make some sound, and we're going to hear it, and we're going to have that spatialized in some sense that we can hear it as if it's coming from that direction. And that may be as simple as panning in a stereo sound field or in a surround sound sense, but also in other ways as well. And so another way of describing this is with Ambisonics. And the difference between Ambisonics and an object-based system is that Ambisonics uses a fixed number of channels to represent the whole sound field. So all the sound that is happening in this room, if I had an ambisonic microphone, would be recorded on 4 channels of audio, for example, if it was a first-order ambisonic microphone. And so Ambisonics give us kind of this mathematical way of deconstructing the audio and storing it, and then no matter how much is going on. It's like a camera for sound. like a 360 camera for sound, I should say. And that 360 format depends, you can get more fidelity, more resolution in space with higher orders of channels. So first order Ambisonics takes 4 channels, second order Ambisonics takes 9 channels, and 16 channels, and so forth. So here we have a stereo track. You've all seen this before. And now this is a first order ambisonic track. So we have the first channel would be what we call the W channel. That is kind of as if it was an omnidirectional microphone. And then each of the next 3 channels gives you some directional information, forward and back, left and right, up and down. That kind of gives you a basis of a first order ambisonic track. And then from there, you can go to second order and third order. It gets a little bit more complicated to describe what the channels are, but the basic idea is the same. We have these kind of decompositions of this spherical audio field. Now, once we have the ambisonics, we need to be able to render it so that it sounds like it's coming, because 4 channels by itself doesn't sound like a sphere of audio. So what we do is we do what's called binaural rendering, which makes it sound as if it's coming through your ears. So there are various things. Here's just a few of them. Head shadowing, so if the sound coming into one ear is louder than the shadow coming into the other, and or has been filtered as it's moved around my head. There's the movement as we naturally cock our heads and move our heads side to side a little bit just to localize sound. You do this almost subconsciously, well, actually subconsciously, and then our ears, our pinna, will affect how the sound is sounding. And all of these and the intraoral time diff, so that the way that when the sound hits this ear and comes to this ear a millisecond or 2 later, that makes a difference. All these different factors play into how things sound for our ears. And so this binaural rendering is an important aspect of how spatial audio is rendered. And this is important whether the sources are objects or whether they are ambisonics. One creative tool that is very important is the ability to also, in addition to having just simple spatialized audio, to also have headlocked audio. Headlocked audio is essentially as if in the real world you're wearing headphones. Wherever you move your head, the stereo channels just stick to your ears, right? So this is a creative choice, but it's an important one because it is very useful for dialogue, non-diegetic dialogue, narration that is not in the scene, so that it doesn't make sense that it comes from any particular place. Music is often, in kind of a 360 video sense, music is often good for this, although not always. And so you can see as we move our head with spatial audio, the sound stays where it is, and as you move, with headlocked audio, the audio follows the head. So both are useful as a creative tool. So here we have a track, a second order ambisonics with a stereo stem as well, so the headlocked audio and the ambisonic audio. So this is what we are able to produce with the Spatial Workstation. There's a bit of a timeline, just to kind of give you an idea of when Ambisonics actually was devised back in the 70s, but it didn't have a commercial success. It didn't have commercial success because it didn't have kind of a killer app. It wasn't really until VR came on the scene and really started to become feasible that VR and immersive media, that spatial audio, Ambisonics in particular, started to be really useful. Because up until that point, we had these really interesting ways of describing things mathematically, but no really useful ways to get head tracking information, for example, was the main blocker to making that a productive thing. So now with VR especially, we have this way of tracking our head and making it a really immersive experience. So if you haven't seen a 360 video, this is just a little blurb, not blurb, this is a little video from National Geographic with Obama in the national parks, and you'll see how the person watching the video is kind of scrolling through the video, and maybe you won't. And then as you listen, and you'll perhaps in this room, depending on the speakers, you may hear some pseudo-spatialization.
Earlier this summer, Michelle and I visited Yosemite with our daughters. We came here to celebrate
That
the National Park Service's
helicopter is
centennial
panned around
and to be
behind,
part
you'll hear
of
the
our
sound
storied
moving
American
around you
tradition
if
of
you're wearing
conservation
headphones.
and preservation.
Okay, so let's talk about how the Spatial Audio App, Facebook itself. First of all, we have the Spatial Workstation, which I mentioned before. These are plugins made with Juice that we use for giving sound designers the ability to create these spatial experiences. We also have an SDK that is a C++ and a JavaScript version of this SDK that are available for people to integrate into their own applications, as we have also done with our own mobile applications and web browser playback experience. This is a screenshot of the Spatial Workstation, some of the pieces of it anyway. So on the left here we have the Spatial Iser, which is, you can think of it as a panner, a 3D panner. So you have horizontal on the bottom, and you also, and distance, and you have on the top you have vertical as well as horizontal. We're taking a 360 video in its equirectangular projection, and then we on the video player on the right have kind of a view into that 360 video. We'll talk more about, Varun will talk more about this in the later slide, but this is what the Spatial Iser, the Spatial Workstation looks like. Of course, in the background, you can see Pro Tools. Once people have created spatial audio videos, videos with spatial audio, I should say, 360 videos generally, then they will want to prepare and for people to be able to hear them. So the sound designer, it's very important to the sound designer to be able to have something that is accurate and sounds accurate. But I mentioned before, there's a lot of different pieces that go into a binaural rendering. And so we feel it's really important to give sound designers the ability to produce content that will sound very much the same, whether they're on in their Pro Tools rig, or someone's watching it on a mobile device, or in the web browser. And so we've tried very hard to make a consistent audio ecosystem where when we produce the Ambisonics, and then we render them in a way that on all of our devices that sounds the same, and that the sound designer can preview. And then in between, the user's ears, the listener's ears, and the sound designer, there's a bunch of steps. Well, so I mentioned before, we have a server encoding pipeline. Once you've uploaded a video, and we're going to make various versions of the video as well as of the audio. We're going to prepare it and get it ready for delivery. We also have to prepare versions for clients that do not support spatial audio, clients that don't support 360 videos and that sort of thing. So we have to kind of consider all the possible use cases. And then for delivery, then we also want to consider bandwidth and what capabilities the devices have and that sort of thing. So those, we kind of make a bunch of real-time decisions about that. And then, of course, the SDK, which is integrated into our mobile devices and web browser playback. So the main goal here is to be able to mix once and deliver it everywhere. So this group here, the Facebook Audio 360 Spatial Workstation group, is a Facebook group for the public to get it's a great community for getting advice, for reporting issues or getting help, and we monitor this group, but the helpful community is also monitoring the group, and it's a great way to kind of get going if you need a little bit of help. In that group, there is a pin post that talks about where to find and download the Spatial Workstation, and where to what you can learn, where you can learn more, videos you can watch, and that sort of thing. So if you're interested in this kind of content, it's a great way to go. And so now Varun is going to delve down into some of the details and talk about some interesting things that we've learned.
Thanks, Hans. So one of the goals of our team is to make it as easy as possible, but for sound designers or anyone interested in the space to make amazing audio. And part of that is ensuring that we've got a really good pipeline for creating content, ingesting it, delivering it to different clients and playing it back, and also serving this huge community that Facebook serves, more than 2 billion users. So we've all got different devices, different platforms, different browsers that they use, and we very much see it as our job to ensure that all of this works seamlessly so that you, either as a Facebook user or as a creator of content, have everything you need to get the job done. But it's also about expanding this outside of the Facebook ecosystem as well. We are in a new market, in a new industry. VR is kicking off into a very exciting space, and everyone needs a room to experiment and find out what really works for this medium, and ultimately what really works well for either your clients or the projects you're working on. And VR by itself has changed to become many things in the past few years. We've seen strong use cases in games and fully interactive experiences, but we've also seen really great projects that treat VR as a linear medium. So you are still watching an experience, you're part of that experience, you're in it, but like a 360 video, you have control of the camera in the sense that you can look around at any time. So you're immersed in what can be a very compelling and interesting narrative that could be a documentary, or it could be some sort of fictional piece. And this is where Spatial Workstation came into play, because we realized that this is a place where there's lots of interesting content being made, whether for VR or not for VR, whether it's YouTube or Facebook, where you can watch a 360 video. And we needed the tools to help bridge this gap and to help people make content, because we all need great content in this new and emerging platform, and we need to reduce the barriers of entry as much as possible. So part of this was also looking at what game audio and object-based audio does really well in fully interactive experiences, and also what we can do really well in a linear sort of workflow, whether you're working from Reaper or Pro Tools or any of the DAWs that you work with. The point here is that you probably spent years, decades working with such software, and you use it every day, you earn your living out of it, and for a good reason. It can be very powerful, in some ways limiting, but also powerful, but especially if you're working with a linear medium, there's a lot you can do with such software. So our goal was to try and bridge this gap as much as possible, to help you work within the software you're already familiar with, but to be able to mix and design content for new mediums, including VR, all within the comfort of your DAW without having to step out of it and jump into other tools. Of course, if you want to jump into a fully interactive game engine type of experience, you can go ahead and do that as well. You, as a creator or a designer or even a developer, have complete control over what you want to do, and more importantly, you have all the options necessary to create amazing content. So the goal with Spatial Workstation was to create this iterative loop. So anyone working with this medium should be able to work with a range of input audio formats, to be able to position that audio in 3D space, and to be able to preview it in real time, whether on their desktop or with a VR device, and really get their creative juices flowing without being hindered or bothered too much by the technicalities of working with new hardware or new mediums. So Spatial Workstation can work with a range of input formats, mono, stereo, multi-channel, ambisonic recordings if you've got an ambisonic microphone, and you can then take all of the information and position it in space. If you work with audio post-production, you're used to this already. You work with music stems, you work with Foley, you work with sound effects, you work with dialogue, each from different sources, different kinds of microphones, and if you're a sound mixer, it's your job to massage all of this data and information into session and ultimately do justice to the script or the narrative or the director's vision. So I'm just going to briefly talk about some of the components in the tools we've got, and then I'll get into a high-level architecture of all the different components we use to bring the tools together, and also how we leverage juice in some of the other components as well. Spatial Workstation by itself has a suite of plugins and desktop applications. I'll just walk through some of them, the most commonly used ones. There's more you can find online if you get into it. The tools are completely free, cross-platform, Mac and Windows. They've been out for a few years now. They're widely used. If you use Pro Tools HT 12.8.2 with the new Ambisonics support that was added in Pro Tools, the plugins are now part of Pro Tools, so you install Pro Tools and you get it. If you use a VST host like Reaper, I'll post up a link later, you can get the plugins from there as well. And we are really excited when we've got people using it and making amazing projects. And we've seen people using it anywhere from VR experiences, linear VR experiences, 360 videos that are posted to a whole bunch of platforms, but also starting to use it as a creative tool to prepare and make content for immersive media, even if it's not a 360 video or a VR experience, whether they sort of ambisonic mixes for AR experiences or even normal games that are not exactly VR based. So it's a really exciting space to be in. And we were quite pleased to see how the industry also responded to this with most of the DAWs adding Ambisonics support or have already added Ambisonics support in the past few months. So the industry has been super responsive to the direction in which all of this is going in. So Hans talked about this. We've got Spatial Iser, which is a plugin where you spend most of your time. It helps you position sounds in 3D space. So on the top view there, you can see me following the character with my mouse. So it's basically the 360-degree video that's flattened out. If you've seen a map of the world, it's a similar projection where you take something that is wrapped around a sphere, like a 360-degree video, but you flatten it out. And you can follow characters in the video with your mouse, and in one shot, write automation. So it's a really fast way to write both horizontal and vertical information, and we then take the data and remap it in 3D space. So in one single automation pass, you can have most of your 3D parameters in place, and then you can use touch automation and also write in distance and some of the other parameters we've gotten there. We also try to bring in a lot of the game audio type of concepts, things like Doppler effects, room reflection modeling, where we also calculate early reflections that are also processed in 3D to help bring this an extra level of immersion into the scene. And we continue to try and bridge this gap in whichever way we can, whether it's with the actual DSP that we've got or even the workflow in bringing more concepts from the interactive world into this linear world. The image on the right shows you all the input formats you can use with the Spatial Iser plugin, multi-channel, mono stereo. You can basically drop it in and then reposition it based on what you see. If you don't have a video, the top view is blank, and you can use the bottom view as a top-down view to then position sounds as well. So while it is optimized for a video workflow, you don't have to use it with a video. One of the cool things with working at Facebook is that we can also learn from lots of other teams who are making amazing stuff. So in the next version of our software, we are using computer vision to track objects in the scene. So in this case, I'm selecting the object I want to track, letting go of my mouse, and hitting play. And we've got our object tracker basically following the object and then writing automation. So what this basically does is it frees up your time, or if you're a sound designer, it frees up your time to concentrate more on your mix and on your design, and let the plugin really take care of the harder work of accurately positioning sound in space. So it's something we're quite excited to release very soon with the plugins as well. Again, to learn more of how we got all these systems to work together, including video and computer vision and all the DSP stuff that happens under the hood. So generally, a Spatial Iser plugin is added to each of your audio tracks. Any audio track that you want to spatialize, you drop it in, position your sound. You can think of it as your panner. It replaces your normal stereo or surround panner, but you're now working with you can call it a more advanced panner that helps you work specifically for this medium. The output of each of these plugins is Ambisonics. We currently use second order, but we'd be also supporting third order soon, where basically what we do is we take any audio that you've got on the input, you can position it in space, and then we convert that we encode it into Ambisonics, which is why accurate positioning is important. So one of the things you'll find is if you generally work with surround sound, which is a channel-based format, and you've got a giant screen, positioning is important, but even if your positioning is off by a few centimeters, you're fine. You don't really notice it because you're usually in a large cinema hall, or even your living room is quite a large space. As soon as you've got a VR headset on and you've got a sound that is positioned wrong and you move your head around, you'll actually hear the sound drifting, which breaks the synchronization that you have with the video. So it's actually quite important to, in some cases, not all cases, to get the positioning to be as accurate as possible. Of course, you can then blow it out of the park and exaggerate your spatialization if it sounds better, but that's when you get into the more creative domain of the space. So the output of each of the Spatial Iser plugins are bused to a master bus, a master aux, on which you drop the control plugin that basically takes the ambisonic mix and renders it into a real-time binaural mix over headphones. We model in a lot of the effects that Hans mentioned, like the head shadowing, the pinna effects, and so on, to give you a binaural render that responds to where you're positioning sounds. So if you've got a sound positioned above you, behind you, and so on, you'd hear that over headphones. We primarily focus on headphones here because with VR and even with mobile devices, headphones tend to be a stronger listening scenario. There are other parameters in the plugins, in the control plugin as well. Find out more when you look it up online. But the basic role of the control plugin is to render your ambisonic mix into a binaural mix. The cool thing here is that the same rendering tech, this very same code, is also used in all the Facebook and Oculus video apps. So what you hear here is what you'd also hear on all the target platforms that you publish to. Or if you use our rendering SDK, which is also free for you to use on any platform or device, you'd end up hearing the same mix. And this is important to achieve a level of consistency across the ecosystem. So something that you'd have noticed with the Spatial Iser plugin is the video. Where do we get that video from? How do we tap into it? We also ship our own video player. It's a 360-degree video player, which you can see me panning around to look around the scene. And that is automatically synchronized to your DAW session. So if you've got our plugins, we share timecode, and our video player synchronizes to it, decodes the right frame, renders it in 360, and also shares that video frame with the Spatial Iser plugin, so it's also shown there, and everything's kept in sync. I'll get into a bit of how that actually works as well. As I pan around the video, you can see the UI in the plugin also changing. We share the camera orientation back with the plugin. So as you look around, you can also hear your mix rotating. Basically, what we're doing here is recreating the end experience that the user would hear, whether they're on Facebook or any other 360 platform. The cool thing here is you can also plug in a VR headset. If you've got an Oculus Rift or an HTC Vive, plug it in, and the video is also projected onto your VR headset. All the head tracking information is piped back into the plugin. So again, you can get this real-time preview of your mix without having to export it out, put it into an app, or sideload it, or publish it. You can get this fast iterative loop happening within your single workflow without having to get out of working of your DAW. So authoring and creating content is obviously one component. The other component is how do you actually get this mix together, how do you get this data together, and how do you publish? This is crucial. If any of you have done post-production work, you know that this is where a lot of confusion can happen, a lot of time can be spent getting all the different formats and metadata and everything else to be correct. So we also ship a standalone application called Encoder. We are very creative with our names, as you can see. You drop in your audio files, also drop in your 360 videos, in this case dropping the ambisonic mix as well as the headlock stem that Hans mentioned. Drop in the video, and then you can export a single muxed file for Facebook or YouTube and some of the other formats and platforms out there. So essentially, you can work with one master mix and extract all these different mixes that you need for all of these different platforms. So in one shot, you can target the major platforms that are out there. And we take on the work of injecting the right metadata for each platform, using the right codecs, and so on. So how does Spatial Workstation work? How is this all put together? Let's jump into a bit of a high-level architecture overview. So we tend to leverage a lot of different technologies here. So we've got a lot of, obviously, DSP work with Ambisonics and rendering binaural audio. We've got lots of stuff happening on the video side because we need to decode those video frames. And then we need to render those video frames efficiently across all the different plugin windows as well as our 360 video player. We leverage OpenGL there. We also need to get information from our VR headsets or the video player again and share that camera orientation information. We use a bunch of networking, and basically we use OSC there as well. So let's look at what that high-level architecture looks like. So if you're working on your computer, you have your DAW. The contrast on the screen isn't all that great, so sorry about that. So you've got your DAW, and you typically have multiple instances of the Spatial Iser plugin, one on each track. So we've seen really complex sessions that have like 70 or 80 or 120 Spatial Iser plugins running to pan all your sound in space. So it's very lightweight. All our DSP routines are SIMD optimized heavily, both for mobile and desktop. So you can run a lot of instances of these without much of an overhead. The output from each of the Spatial Iser plugins is then sent to the control plugin, as I mentioned. So all of this is very much a typical DAW workflow. You've got all your plugins as they are. They work as they should. They get audio in. They get audio parameter data in. They process it, spit the audio back out, and that's what you hear out of your DAW. But we've also got our 360 video player, as I mentioned. Currently, this runs as a separate process. We might be changing that in the future, but it currently runs as a separate process. It's an OpenGL-based application where we can display video frames in a 360-degree view. What we basically do there is take a video frame and wrap it around a sphere and put the camera inside the sphere. So as you look around, you're basically seeing. You can think of it as a projection in a dome theater or something like that. If you've been to one of those, it's a similar concept. But the video player is really a light front end for media server. As I mentioned, we're very creative with our names. Media server is basically in charge of decoding video, decoding video frames to a largish buffer, about 60 frames or so, 60 to 120 frames, depending on the size of the video. It can also decode up to 4K video, but we generally recommend about 2K as a common workflow. So that by itself can be an intensive process. So the media server decodes all of this data to a buffer in shared memory. It's a FIFO, basically, first in, first out. And that data is then uploaded to an OpenGL texture. We take those pixels, create an OpenGL texture out of it, and that's what's mapped on this sphere, and our 360 video player. We also use a second texture where we map the same where we upload the same data to a second texture that is used in an OpenGL renderer that is shared across all the plugins. So we've got a shared GL context that you can think of it almost like a GL singleton. If any of you worked with GL, you know that can be a nightmare. But we got it to work really well. So what we basically do is we upload a single texture, and then we share that single GL texture across multiple OpenGL contexts. The reason we did this is we had to be efficient. Uploading a 2K video is significant amounts of video memory. And if we had to create a new texture for each plugin that opens up, that would be a lot of memory. And uploading pixels from sort of the CPU to the GPU can be very intensive as well. So we want to reduce that as much as possible. Even in this case, I think we've got one too many textures. Ideally, we should just be using one and getting our job done there. So the GL textures for the Spatial Iser plugins are shared, so we can minimize CPU costs there and only upload a texture once for every time a frame is changed. But how do we keep things in sync? So our plugins send timecode information over OSC. We do so over OSC. I'll explain why we do that in a bit. It'll make a little more sense. But we share timecode information over OSC to our video player process, which then passes that down to media server. And media server receives a new timecode and decodes a frame for that timecode. So if you've got continuous playback, we're sending continuous timecode. Media server receives timecode information, decodes those frames to shared memory, which is then uploaded to textures by video player and the Spatial Iser shared renderer. But we also need to get information back in, where we've got the camera orientation as you're looking around the scene. That is also sent back to the plugins over OSC. We use OSC because it's simple. In the future, we hope to publish a spec for it. So if you don't want to use some of our components, you can replace it by another video player or a head tracker device or something else. So it's fairly straightforward to use OSC there. But alternatively, you can also use a remote computer. So video decoding can be expensive, especially if you're using large video files. But more common in post-production, you've got computers where you basically got post-production setups where your main computer is often a machine room somewhere, and you're nowhere close to it. So it helps running the video on a separate computer. And this is where the OSC setup helps, because you can then over LAN set up the video player on another computer and then synchronize everything by sending timecode and receiving camera orientation over OSC. So basically, we can change our data endpoints quite easily. And if you've got a VR headset that hooks up to the video player, and if If we detect VR headset, a supported VR headset is connected, we then override the camera orientation information there and pass that down to our plugins as well. So you can think of the VR headset and the video player and the Spatial Iser panner that's got the video as really simple OpenGL endpoints. And most of the work is really done by media server and ensuring that it decodes the right frame, the right time. We try as much to, even within this structure, to have a tolerance of about 1 frame, even in worst case scenarios, for synchronization. So that's the visual stuff. So a lot of the UI, and we leverage Juice for basically the general plugin architecture, the UI, and as well as some of the OpenGL stuff. But we've written our own OpenGL libraries around the basic tools that Juice provides to get all to share our textures and everything else between our processes. So basically, Juice acts as a simple sort of front end to glue all our different libraries together. We've got a spatial audio library that's been built over many years. It's heavily SIMD optimized, Neon, SC, AVX, all of that. And if some of you were at the SIMD talk this morning, we use a similar technique in the sense that we do compile time optimizations wherever possible to ensure that we use the right instructions or the optimal instructions at the right point. Spatial audio libraries is basically a C++ API for our internal use, where we can then do object-based audio rendering, Ambisonics, simple early reflection modeling that's used in the plugins, or we can even do complex sound propagation as well if you've got actual geometry like what you might see in a game. Then we've got a video and graphics library, so media server is part of this. So being able to decode different videos and different resolutions, keeping all of that in sync, background uploading of the texture to shared memory, and also VR headset integrations. And last thing, a networking library for OSC. But something else that we've started doing recently is we built up a new library called UI Server. Again, an amazing name, which was actually a project for us to start using React as a UI front end for our plugins. We've made some amazing progress there, and probably next year at next ADC we'll have something to share there. But the side effect of that was we actually had a server where that would be hosted on your local host, running your plugins, but we can also use that to start sharing parameters between different plugins. So we can if you change a parameter on a single instance of a plugin, we can mirror that change elsewhere and show it on another UI in another process even, which allows for a lot of flexibility. So we can now visualize and control parameters from almost anywhere that we want to, as long as we connect to the server. It could also lead to some future extensions that are possible, like also controlling that, say, from a phone or any other device. You just need to connect to the server and send the right parameters. So there's some interesting lessons to watch out here, because we do everything from sort of data level parallelization like SIMD to multi-threaded parallelization, especially with OpenGL, which can get complicated because OpenGL by itself the API is designed to be single-threaded. And we also got multi-process parallelization as well. So lots of interesting lessons there. One is we try as much as possible to stay away from mutexes and locks. It can lead to a general debugging nightmare, but at the same time, we want to keep things in sync, but we also want them to be low latency and as fast as possible. So we achieve this using we use Atomic a lot, at least for primitives, especially if it's one-off things that we need to write to and read to. If you haven't used Atomic, lots of great material online, including, I think, some talks from ADC as well as CPPCon on this. This is worth spending anybody's time if you're working in a multi-thread system. Write or use a good lock-free, non-blocking library for sharing data between threads. We've got a really good library that we wrote that can deal with single producer, single consumer queues, basically a circular buffer that where you can have one writer on one thread and a reader on the other thread, to multi-producer, multi-consumer queues where you can have multiple readers and writers, but still using a lock-free structure. And of course, more threads does not equal to better performance. DAWs can be complicated, especially if typical user is going to have lots of plugins, a convolution plugin, a sampler. The DAW by itself might be using a whole bunch of threads for disk streaming and anything else that might be happening. So in the simplest of case, your plugin might be performing really well, but when you actually load up a large session, it would start to lag. This is the single most important line of code across our code base, especially if you're working with multi-threaded environments where basically you assert to check that you're actually calling the code on the right thread. Because with complicated C++ structures, it can be very hard to guarantee this. And all it requires is somebody who's unfamiliar with this piece of code to just go and call a function, and the next thing you know, you've got data races happening all over the place. Your plugin doesn't run in a vacuum. We wish it could, but it doesn't. We still need to depend on the DAW for the functionality it provides. The plugin still needs to communicate or work with other plugins. And ultimately, really needs to perform well, because if an average large Hollywood-type session is going to have hundreds of instances, or even, say, about 100 instances, it needs to be really performant. Uploading video text pixels to texture can be really, really slow. There are lots of efficient ways to get around this, lots of different techniques out there. We've kept it really simple, mostly because the video is in a format that is easy for post-production. So we try and reduce this as much as possible, and as I mentioned, only use 2 textures. And very soon we want to bring that down to 1, to just use 1 texture across everything. Writing a good video decoder is hard. Keeping things in sync, keeping video in sync is really important for post-production, and doing that is hard. It took us, I'd say, multiple iterations over a couple of years to get it to a state where we really like where it is, and that took a lot of hard work. And we try and defer all transformations, if possible, to OpenGL. So typically, a video decoder is going to give you frames in a particular format, and then you need to convert it to get your colors to show up correctly, and so on. We defer all of that to a single OpenGL shader, so we can do everything in one shot on the GPU without taxing the CPU. So let's take a step back and look at the full signal flow, taking this architecture into consideration. So you have multiple Spatial Iser plugins in your DAW that output Ambisonics. Go to your control plugin. You can monitor binaural mix. You could also have mono stereo tracks using a normal stereo panner in your DAW. And that's for your headlocked audio that you do not want to rotate within the scene. When you're done with your mix, you'd export out your ambisonic mix, and then you'd export out your headlocked mix. So essentially, you'd end up with 2 stems, 2 master tracks. And that you then drop those stems with the video into your encoder application, into our encoder application, and then you can output to Facebook, YouTube, and some of the other formats as well. If you're uploading to Facebook, you then go to Facebook, upload that video file. That would then hit our ingestion and transcoding pipeline, and then we would serve based on a complicated set of rules, as Hans mentioned, based on the device type and the endpoint and available features. We would then stream it down to all of our different clients. So that's the Facebook Android app, the iOS app, Oculus Video, and web as well. All our native platforms are backed by our C++ audio SDK, which I'll talk about quickly in a bit. And our web audio playback happens with a combination of mscript10, where we transpile our C++ code so we can use the same code base everywhere, and web audio components. So let's briefly dive into the audio SDK before I wrap up. So just like how we've, similar to Spatial Workstation, I'll talk about the architecture there. So basically, it's a really simple C++ SDK to help you create an audio engine and play back spatial audio, whether it's mixes from your ambisonic mix from the Spatial Workstation, or including mono or multi-channel audio that you might want to spatialize within a scene. You basically open files, hit play, and then you can synchronize those streams to external time sources like a video player, or you can also just treat it like a normal audio engine, and you don't have to deal with OpenSL and Wasapi or any of the sort of back-end integrations into operating systems, it takes care of that. So yep, I mentioned all of this. We've also got support for game engines. So if you use something like Unity, we've got a C# wrapper for that as well. Performance here is key, especially when you're running at Facebook scale. So this is a basic comparison. If your video takes about 100% of CPU, the audio engine takes less than 3%. So it's basically, there's no excuse not to have good spatial audio playback. Something that is important that I found since joining Facebook was binary size. We don't want to bloat the app. It's really important to ensure that our library is really, really small, but also performant. Optimizing for size is way harder than optimizing for speed. And so you can compile the library in some configurations down to 150 kilobytes. So you can still get that good performance at a really small size footprint. Oh, that's an unanimated arrow. Right, so I just want to talk about the high-level architecture of the audio SDK as well. So you've typically got a main thread where you can basically interface with the engine, control playback, create and destroy objects, and so on, set the listener properties like the camera orientation and so on. Got an audio thread that's usually handle and interface with things like Wasapi, Encode Audio, and OpenSL on Android. That does all the mixing and audio spatialization. Got an event thread for signaling events like the state of the decoders, errors and debugging, transport like this file has stopped playing. We've got a decoder thread that does all the I/O and decoding of codecs. So the typical flow is the user calls APIs, and they also receive callbacks from the event thread. All events from the main thread or whatever thread the user calls certain APIs from communicate to the audio thread through a lock-free queue. Same thing happens with the decoder thread as well. And the decoder thread and the audio thread communicate to the event thread again via a lock-free queue, so everything's lock-free, thread safe as much as possible. And the decoder thread also communicates to the audio thread via a lock-free queue again. So we use the queues to transport both events and data across the system while ensuring things are lock-free. So you can find out more by hitting those links. Spatial Workstation and the SDK is available there. You can join the Facebook group that Hans mentioned. We're really proud of the community that has built up around this in the past few years. Lots of really interesting projects that have come together. And we're really proud of everything that's come around. And we continue to work in this area and make lots of improvements in what we do. We recently spent a good chunk of our research time in measuring loudness within a 3D or an ambisonic field. We shipped a plugin. So if you download Spatial Workstation, there's a specific plugin for measuring loudness. So there's lots of other areas and important things that we're getting to. And we also get a lot of feedback from the community, which has been awesome. So that was it. If you've got any questions, we'd be happy to answer them.
Okay, we probably have time for a couple of quick questions, if anyone wants to ask. Yeah.
Hi, thank you. And I would like to know a little bit more about the HRTF you are using, and also if there is the possibility to change it, either for monitoring or for final delivery.
Yeah. So currently, we do not allow for the HRTF to be changed, mostly because if we allow it on the if you can change it on the tools, how would we change it on the application side? Is the average Facebook user going to upload an HRTF or capture an HRTF? That's a big problem, and that's not an easy problem to solve. I'd say the technical component there is easier, but the actual user experience is a more complicated problem. So currently, we do not allow for a custom HRTF to be uploaded. The HRTF we use is something we built over many years, so and that is something we haven't shared yet, but when we do, we will.
Okay, anyone else? Yep.
Might there ever be a possibility of doing a speaker decode from the web tools?
Somebody else asked us this, I think. Yeah, so currently, no, we just decode the binaural. We're going for the primary use case, but if that comes up in the future, potentially.
And anyone else?
Hey there. Oh, wow, that's loud. Just quick question. Can you, I mean, not, it's fine if you don't, but can you outline future features that you want to implement other than the following the image recognition or following the spot sources, or?
Sure. So a few things that we've already spoken about is you can use the same ambisonic mix to also do 6 degrees of freedom movement as well within a limited capacity. So you can not only do orientation, but you can also move in the mix a bit. This is a feature we've had for a while, mostly in our SDK, but we're making that more prominent now. Other than that, we haven't really announced anything specific we can share, I think.
Okay,
Yeah.
thanks.
Yeah, but we typically tend to have new stuff every few months, so the group is the best place where you'd see it.
Okay, one more here.
Hi. Just on HRTFs, do you see the future in individualized HRTFs or in a one-size-fits-all?
That's an open debate. I think there is a future in personalized HRTFs. How we get there is still unknown. The process for getting there, not just technically, but also, as I mentioned, from the user experience. The win for us would be if we can do this for everyone who uses Facebook in a way that's non-intrusive and easy to use. That would be sort of the holy grail. But yeah, I think there is a future. How we get there is still unclear. There's lots of interesting research happening across the industry as well in this area. So I just see what happens.
Okay, and one last one.
I'm curious about your comment that sort of binaural or headphone only. What do you think about with respect to musical recordings, for instance? I see a lot of applications about rather than needing to actually attend the concert, to be able to buy a season's pass to the Berlin Philharmonic or something like this. So do you insist that it's headphones only, or do you see a wider use of that?
Do you know? Oh, okay, I'll answer that. Yes, I don't think we're close to any other rendering technologies. If speaker-based formats are important to the people who use what we do, then we definitely consider it. Totally open to options there.
Well, another thing about speaker-based formats as well as HRTFs, for that matter, is that now that we've been able to move to actual second-order ambisonics instead of the previous hybrid format that we used, we're able to interoperate with other ambisonics plugins or workflows, right? So if you have an existing second-order, speaker rendering or HRTF rendering or whatever, you can just kind of like drop that in place after the control plugin, and it will just be available, and you'll be able to iterate with that. So that kind of is maybe a little bit of a punt, but that's a bit of an answer there. I think my own personal opinion on music, I think that's why Varun was offering here. I think that music it gives, especially in kind of a context of kind of music that is live and has like this idea of some positioning. You got people kind of here and there, and being able to experience that in a way that's very natural, I think comes really well. And speaker rendering is one way to do that. I think I'm hoping that kind of within a few years we may see some head trackers that have become very affordable and easy to use, and that might provide an option, a way for experiencing this, even if it's not tied to a 360 video and not wearing a big VR headset, but maybe just like a little thing you attach to your headphones, and suddenly you have a kind of a I'm there experience, even if I'm just listening. So I'm excited for that.
All right, that's all we have time for. So once again, thanks Hans and Varun.
Thanks.